Hey y'all, and welcome back to Coding with Minmer. On today's agenda, we're going to tackle LeetCode 708, but with a TDD approach. That's right, we actually have a golden opportunity to practice a bit of engineering and good practices. As always, we'll go over a variant afterwards, but as you'll see, because of our healthy suite of tests, we'll be so confident that our extended code still works. Let's get started. We're given a circular linked list node, which is sorted in non-decreasing order. We want to write a function to insert a value insertVal into the list such that it remains a sorted circular list. So, taking a look at our example here, we clearly have a linked list. Wait, something's off. That's right, it has to be a circular linked list, and thus needs this pointer. Another important property of this now circular linked list is that it's sorted in non-decreasing order, meaning from one node to another, there's either an increase in value from this 5 to 10, for instance, or the value remains the same from 10 to 10. As for the rest of the nodes, they're clearly increasing in value, except notably the rightmost node, where we loop around and decrease in value from 20 down to 5. It's technically a disruption in the overall order, but this is allowed. As we saw, it's necessary to make our linked list circular. Like the problem description says, we're also given an insert value integer. We're tasked to create a node of it and integrate it in such a way that our circular linked list remains sorted. Like so. We should note the given node can be a reference to any single node in the list and may not necessarily be the smallest value in the circular list, meaning the input head node can be node 5, 10, 10, 15, or 20. It's fair game. Arbitrarily, we'll say that node 5 is the head, sure. Reading on, if there are multiple suitable places for insertion, you may choose any place to insert the new value. After the insertion, the circular list should remain sorted. Translating this, if we had an insert value of, say, 10, then there are 3 places to insert it, either here, here, or here. As a last note, we could be given a node that is null, in which case we should create a single new circular list and return the reference to that single node. Otherwise, return the originally given node. To see this visually with an example, we'd create a node of apparently integer 60, set its next pointer to itself, and then call it a day. In either case, we return the head node as our answer. So here, since we have a single node, it serves as the head. That's what we return. In our first example, if node 5 was the head, then that's what we return. That's our answer. Okay, cool. We have an understanding of the requirements, or at least some of them. We observe there are a lot of cases to consider, which is why TDD would be an attractive methodology. Therefore, for our approach, we'll cycle between writing failing tests, only to then fix it with implementation code, and then doing it all over again, all the way until we've covered all of the requirements. Great, so what do we already know? We already witnessed the happy path test case, as well as the test case in which the input node is null. But what if we had to insert a node in this awkward no man's land where it wasn't sorted? We went from 20 down to 5. My intuition tells me that I need different code if we had to insert a node with a value of, say, 9,000 or 1. I'm unsure what the implementation would be, but I shall cleverly name this test case the out-of-range test case. That's all the ones I can reasonably come up with. Maybe I'm missing something, maybe I'm not. Either way, let's start writing code. Test code. Let's kick things off with the happy path test case and bring back our beloved example. As we saw, we're given the head node as node 5, sure, and we had to insert a node of integer 19. It's a no-brainer that it should belong in between nodes 15 and 20. After the operation is completed, we should assert that from our head node, the entire order remains intact. So increasing or constant. To remind you, a singular decrease is allowed for our circular linked list to be circular. Manifesting this as a test, we'll conjure up a head node with a value of 5, and then after it, a node of integer 10, and after that, another 10, 15, and then lastly 20. Note that node 20 loops back around to the head node. We'll initialize our system under test, and with it, invoke our insert function, passing in our two inputs, the head and an integer of 19. The return type, remember, is the head node, with which we'll verify with the head node's memory address. They should be the same exact thing, and therefore have the same value of 5. We're not done yet though. Let's make sure the following nodes are in the order we expect them to be. The next node after the head should be node 10. And after that, another duplicate node 10. And then 15, 19, 20, and lastly, back around to the 5, where we began. We need this last assert to make sure our code didn't wrongfully mutate the pointers. And if we run this, no duh, it fails. For the next step of TDD, let's come up with a solution and then write the implementation to make this test case work. Any ideas? I'm all ears. But to start, we observed that we should have some sort of check to see if our insert value, right here, is ever in between its previous node and the next node. Sounds logical, but the name next may be confusing since the pointers aren't named next. So why not something like current? C for current node. Of course, we won't magically know to insert our node right here. We'll need some forever loop that keeps going, and on each iteration, execute this if statement of whether 19 is in between our pointers. We can choose to start the previous pointer at the head and the current one right after. Is 19 in between 5 and 10? For those of us who skipped elementary school, the answer is no. So let's continue this loop and move both pointers along, previous to current and current to its next node. Now, is 19 higher than 10 and also lower than 10? Obviously not. We'll progress our two pointers. I must apologize for the Dora the Explorer vibe, but once again, 19 is not in between our two values here. But on the next iteration, we see a glimmer of hope. 19 is greater than the previous node, but lower than the current node. Finally, we get to spin up a new node with the value of the insert value, set previous next to the new node, and from it to current. Ultimately, we return our head node of 5. Sounds fine so far to me. Let's code this up. To start, we'll initialize a local previous and current pointer to the head and head next, respectively. Let's start our forever loop, which is just a while loop that goes on endlessly until we find the right insertion spot. On each iteration, we have an if statement. Is the previous node's value less than the insert value? And is the insert value less than the current node's value? If so, we'll create a new node with this integer value, set the previous node's next pointer to it, and don't forget, we need to set the new node to the current node, the one after. If you're curious, this is part of the nodes constructor, observed right here. After the deed is done, we return the head. And of course, if we haven't incorporated insert value yet, we'll move both pointers along. And if we run our tests, nice, amazing. Okay. When I was going through this walkthrough, I remembered there can be multiple places to insert a node, right? If we had an insert value of 10, then recall there were 3 opportunities to integrate node 10. It was here, here, or here. It doesn't matter where, so as per our existing logic, we just insert the moment we can. Right here, of course, between our pointers P and C. However, this implies that our if statement won't work. 10 is technically not lower than 10, so we'd skip this insertion opportunity. Instead, we need to modify our logic to see if insert value is greater or equal to the node before, as well as lesser or equal to the node after, pointed to by the current node. We fail to have this circuit breaker in place, and because of that, we'd be going in an infinite loop. Now, the benefit of using TDD is that we can prove that we need this logic, and if it turns out we don't, then that's bloated code that we never needed. So let's repeat our nature of work. Let's write a test case and copy and pasting our other one and change what's needed. We don't need to recreate the solution class. We'll now insert an insert value of 10 and modifying our assert as necessary. We'll count for another added node of 10, shifting everything down. And if we run our tests, how much time do you have? We clearly have an endless loop. Let's quickly address this concern, and in our code, update our equality signs for correctness. And after we do that, run our tests once more and confirm that we fixed the issue. Nice. And I will say, what we currently have dangerously assumes that we'll always have a place to insert. But don't sweat it, we'll address more requirements in the subsequent tests. Moving on, this was subtly mentioned when reading the problem description, but recall there's one place where a circular linked list may not be sorted. This is okay though, it's part of the data structure's definition. In this example, we're non-decreasing until we're not. When we go from 9,000 back down to 420. What's the point of this? I'll tell you right now. If we had to insert a value that's larger than the largest node, or a value that is smaller than our smallest node, then they can only be inserted in this no man's land and thus retain our weird exceptional decrease. The big question is, would our existing code accommodate for this? There's only one surefire way to find out. Let's write a test case and see if it passes. We'll call this one tests out of range. We'll arrange our inputs first, which I didn't mention it, but node 666 would be the head for this example. Let's simulate our visual exactly. 666 points to 9,000, which points to 420, back to the head. We'll act on our system under test by invoking our insert function, passing in the insert value of 9,500. And alas, we'll assert that the head is what we actually returned, and more specifically, that it has a value of the expected 666. After this, 9,000 should be the following node, and after that, the new node, and then the 420, and then we wrap around in our circular linked list, back to the head 666. And while we're at it, let's do some copy and pasting and account for the case in which the insert value is lower than the lowest node. We use 10, so let's update the asserts as appropriate. Instead of 9,500, it'll now be 10. And silly me, let's not assign, let's compare. Okay, moment of truth. And we have ourselves another infinite loop. Somewhat expected. Going back to our example, no matter how many times we move along our previous and current pointers, we'll never actually get to execute our if statement to insert a node. As a natural response, let's spontaneously throw code at the wall and see what sticks. That if our previous pointer is at the largest node, and our current pointer is at the smallest node, and we know this when previous is larger than current, and the insert value is greater or equal to this largest node, 9,500 is bigger than 9,000, or the insert value is lower or equal to the smallest node, 10 is obviously lower than 420, then we'll mimic our logic from before, spin up a new node, and rewire these pointers. Great. In the code, let's introduce this new if statement. If the previous node's value is greater than the one that the current pointer is pointing to, and our insert value is greater or equal to the previous value, or the insert value is lower or equal to the current value, then we'll do the same exact thing as above. Create the new node and rewire as appropriate. Running our tests verifies that we're not crazy. Good job. There's something satisfying about seeing green passing marks. Moving on to our last test case, we can be given a null head as input. I think I may have been called that once or twice before. But anyway, this should be small beans. My thinking is, if we go by our code, we'd initialize a previous pointer, sure, but then incur a null pointer exception when we try to set the current pointer. Obviously, there's no node after the null pointer. This edge case sounds like it needs a good old manual if statement. The problem description pretty much procedurally instructed us on what to do. We'll spin up a new node with integer 9000, set its next pointer to itself, and return the created node as our answer. As per our test-driven mindset, we're supposed to write a test, note its failure, and then supplement our code to then make it all work. Yeah, I can do this, but this is where I find a bit of overhead complexity in the TDD approach. In the case we know exactly what the required logic should look like, I say YOLO, skip all tradition and ceremony, and just do it. That, if our head input is null, we'll instantiate a local node object, set it to itself, and then return it. Confidently, we'll write our test case, in which we'll first need our class. We'll invoke our function of interest with a null node, ensure a value of 9000. It doesn't matter what it is. And we get back the head. We'll verify that its value is indeed the 9000. We'll also make sure that this node 9000 points to itself. Running the tests. Boost my overinflated ego. Fantastic. Everything works how it should. Alrighty, we're done. Let's collapse our tests, clear our whiteboard. What's this? No, please don't. Okay. Thanks for more work, I guess. We were just given another example and a corresponding test case. Okay, fine. I'm sure our logic works anyway. Or you know what? Let's go over the example for good measure. We're supposed to insert a value of 1 into a circular linked list full of duplicates. From what we already know, we can freely insert node 1 anywhere, right? Here, here, or here, it doesn't matter. As the why it doesn't matter, recall the counterintuitive definition we established with our data structure. Every node must be non-decreasing in value except potentially one spot. This is all to say we have enough context to generalize that any of these spots are fair game if every node is equal. Of course, according to our current implementation, we have no choice but to go into our while loop. Really though, we have no choice. We won't know that we only have duplicate values of the 7 in this case if we don't go through every single pair of nodes. Thus, our goal should be to find an opportunity to break out of our loop. To build some intuition on how, why not do a quick walkthrough with what we currently have? Good idea, Min. We'll spin up our familiar P and C pointers. P at the start and C right after. We'll start our while loop to ask, is 1 in between 7 and 7? No. So we move both pointers along. And repeat, is 1 in between 7 and 7 now? Still no. This iteration is no different. And we're kind of back to where we started. And we know that because previous points to our head, which if you recall is where it originally began. Hence, we have an infinite loop. Wait, that's useful information, right? If our previous pointer makes its way around our whole circular linked list and points to our head input, then we can break out of our while loop. Combining this with our earlier knowledge, if we can insert the node anywhere, can't we just insert it in between wherever P and C ended up after the while loop? And if we terminate our while loop when P equals head, then the new node will always be right after our head. And you may be wondering, don't we always start previous on the header? Wouldn't we break out on the first iteration? That's fair, but it's an order of operations kind of thing. That after we discover that 1 is not in between 7 and 7, we can move both pointers along before we check if the previous equals head. Specifically, our logic should go right after this line. After we move prev to cur and cur to cur next, we'll check, does prev equal the head? If so, we have a linked list full of duplicates. Let's break out. Before we move on, let me just collapse our test case. But anyway, having broken out, let's do the usual creating and setting, and eventually returning the head. One last hurrah. Amazing. Yes, we are actually finished, but there was one step of TDD I intentionally excluded, and that's the refactoring part. We chose to use a TDD approach, and because of that, we have the minimal piece of logic that is functional, but it doesn't necessarily correlate with the fact that the code is clean. Let's do some refactoring, but I will quickly mention, it's because of TDD that we have a comprehensive suite of tests. If we ever modify anything that's breaking, we'll know, and that's because the tests will scream red. The first thing I notice is that we have duplicate lines of code, namely lines 14, 15, 17, 18, and lines 24 and 25. These two. What I'd rather do is break out of the two first cases, fall back to lines 22 and 23 as the centralized place to do the same exact functionality. This is a bit more concise. To make sure that we didn't regress any modules, we'll run our tests, and everything still passes great. The time complexity is big O(n) because we'll make at most one pass over our circular linked list. We terminate our loop the moment we make a 360. The space complexity is big O(1) since we only use two pointers, P and C. Cool. Let's take a look at the variant. Welcome to the variant, where there is a teeny tiny cutesy change. Let me direct you to the sentence of interest. We want to now return the reference to the newly created node. This sounds like a trivial change in requirements, and that's because it is. I will warn you, if you're straight up memorizing LeetCode problems, then this variant was meant for you. Please be careful. As to how we tackle this, we'll leverage our TDD approach and simply extend it for this variant. Okay. So if we should be returning not the head node, but the newly created node, then the first thing we have to do is change all of our tests to reflect this new requirement. Taking a quick look at our tests, that's quite a lot to update. And it's true, TDD has its costs. I'd be lying if I said maintaining tests wasn't a pain sometimes. But also, if the requirements of a feature at a real job completely changes from under us, and trust me, they can, then it can be very time consuming on us developers. But anyway, let's suck it up and fix our tests. And done. That took a few seconds, no sweat. It goes without saying, if we run our tests, then we should see a lot of red. Yep, that's what we expected. To fix this, let's look at our code. If our head pointer is null, then we still return the created node. This just works out, nothing to modify here. For the other three cases, we note that we find an opportune spot to insert the newly created node. We'll simply break out of our while loop, where we'll then have a centralized place to do the inserting and then the returning. Specifically, we set the previous node's next pointer to the newly created node. And if it points to the newly created node, then shouldn't we just return it? Yep, let's do that. The return of prev.next. In retrospect, thank goodness for our refactor. Because of it, we only had to change one place in our function, not three. To ensure we got the functionality correct, let's run our suite of tests one last time. Good stuff. And look, I know a lot of code bases are, for a lack of a better word, spaghetti and or legacy, but as long as it's moderately tested, I'm sure there aren't many nightmare bugs and regressions. And if you learned something today, please make sure you like, comment, and subscribe. Thank you.